Hello everyone, this video is part number 2 of implementing the ready pin in our databus demultiplexing circuit. I suggest you start with part number 1 if you haven't watched it already, but if you did, I hope you enjoyed this one. So in the first video, we took a look at the ready pin of the CPU and discussed how it could be useful to hold the CPU during DMA access. And we started by turning it from a bidirectional signal to two unidirectional signals. One which is an output that tells us when the CPU is waiting internally after executing the wait for interrupt instruction, and one input for when we want to stop the CPU ourselves. So let's keep looking at the ready pin. A low input logic level will hold the microprocessor in its current state, and returning ready to the active high state releases the microprocessor to continue processing in the next clock negative transition. So what does it mean? If you look at the KiCad section in the datasheet, there is a note on the databus/bank address operation when ready is pulled low. And it says that when ready is low, the databus is held in the data transfer state, i.e. the clock is high. So what this says is when you pull ready low, the CPU will be stopped as if the clock were held high. It will continue transferring data. This is an interesting property because it will help us connect the CPU to slow devices. For example, our ROM is quite slow, and so it would be nice to be able to run the CPU at a high frequency while still being able to connect to the ROM. And so what we could do is to introduce a wait state in which the CPU would be held in the data transfer state by using ready. Okay, so let's take a look at how the ready pin works conceptually. So I have here the clock signal. Let's see what happens internally to the CPU when we use the ready pin. So let's say this is our ready pin. We can see that initially it is high. Then during the first clock cycle, we bring it low. We keep it low for a clock cycle. And then in the third cycle, we bring it high again. It would be interesting to look at how the internal clock of the CPU behaves in this case. So this is a representation of the internal clock of the CPU based on the description from the datasheet. So you can see that during the first clock cycle, the CPU is executing normally. But then remember the caveat on the datasheet that said that when ready is low, the databus is held in the data transfer state, i.e. the clock is high. Conceptually, that means that the internal clock of the CPU is kept high. So in the second cycle, when ready is low, we can see that the internal clock of the CPU doesn't transition and is just staying high. Then in the third cycle, we see that in this example, we bring ready high again. And in the datasheet, in the description of the ready pin, it mentions that returning ready to the active high state releases the microprocessor to continue processing following the next phi 2 negative transition. So in the next negative transition, which is here, the CPU will resume its activity, and so the internal clock is enabled again. And so you can see how this can be useful, right? Because if we want to access the bus, we can stop the CPU internally and then resume its activity. If we want to access a slow device, we know from the timing diagram that the CPU is reading and writing on the falling edge of the clock. And so we can set up the slow device on the first cycle here. We can give it plenty of time to read or write the data, and then read and write happen when the CPU resumes its operations. So this is really useful. So how could this impact our databus demultiplexing circuit? Well, if we want to use the ready pin in order to introduce wait states, we have to keep the external components of the CPU in the same data transfer state, which means they should behave as if the clock is maintained high when ready is pulled up. So in the past two videos, we have built this control circuit for the demultiplexing of the databus. Let's see how it evolves if we add the ready pin as an input. So this is our truth table where we left off in the past two videos. Let's add an input for the ready pin and see how our control signals will have to evolve. Okay, so I've added the colon for the ready pin. And when ready is set to 1, this is equal to the previous behavior. Let's see what our control signals have to look like when ready is pulled low. So the easiest is the output enable of the latch. When ready is brought low, the output of the latch shouldn't change. It should keep outputting as long as we don't bring bus enable low as well. Then there is the latch enable signal. If we look at the timing diagram, when the clock is high, which is the state that we want to maintain externally, the latch enable signal is low. That's when the latch will keep memory of its inputs and keep outputting the bank address. So that's what we want. We want the latch to keep outputting the bank address when ready is pulled low. So the latch enable should be low in all cases when ready is low. And then there is the output enable of the buffer. And for that, we can take a look at the timing diagram, and we see that when the clock is high, the output enable of the buffer is kept low. And that's what we want because we want it to be kept in the data transfer state. When the ready pin is taken low, we should keep the output enable of the buffer low. But that's true only if bus enable is high. In the other case, when bus enable is low, we want to disable the output of the buffer. So this is our updated truth table. Let's take a look at how the logic formulas will evolve. The output enable of the latch is still the inverted bus enable signal. There is no change to it. Then if we look at the latch enable signal, we can see that it's still the invert of the clock, but only if ready is high. So we should end ready with the inverted clock. And then the most complicated one is the output enable of the buffer. It's either bus enable is low or the clock is low and ready is high. So bus enable is low or the clock is low and ready is high. Okay, so this is the new control logic, implementing using logic gates. You can see that it's quite a bit more complicated. We now have an AND gate and an OR gate, as well as 2 inverters. And so we're going to have to add a couple more components to our circuit. But more importantly, what I'm interested in is keeping the timings really tight, because as we saw in the previous videos, we have this 10 nanosecond window here for the latch to memorize data. And similarly, we don't want to keep the buffer enabled too long after the falling edge of the clock, because then the CPU will start outputting the bank address. Basically, what that means is we want to minimize the number of gates between the clock signal and our control lines. And so it would be nice if we could remove this inverter here so that the latch enabled signal only has 1 gate between it and the inverted clock, and then the output enable of the buffer has 2 gates. I think that would be okay because it's a bit less sensitive. And so to be able to remove this inverter gate, we have to generate the inverted clock. And what we need is for the inverted clock to be perfectly synchronized with the clock. So there's a pretty easy way to do that, and that is to use a D flip-flop configured as a frequency divider. So if you look at this circuit, you can see that we have a D flip-flop here with a feedback loop. The way this works is every time the input signal goes high, the Q output will be set to what is at the output. And so if we look at the signals here, we can see that what this does is that every time the input signal goes high, the output toggles. And so this results in a frequency division by 2. But what's interesting is the D flip-flop has this property that its output and its inverted outputs are always changing at the same time. So they are perfectly synchronized. And so we can take the output frequency here as the clock, and we will automatically get the inverted clock at the inverted Q output in a synchronized way. The only thing we have to keep in mind when doing this is we have to input twice the frequency that we want. So for example, in order to run the CPU at 14 megahertz, we would have to input 28 megahertz into the D flip-flop. So we'll have to keep that in mind when we're building our clock circuit in a future video. So if we add this flip-flop to our clock generation, so we can remove the inverter because we now have the inverted clock, and we know that the inverted clock is perfectly synchronized with the clock. So in terms of the timing, it should be much better. So one additional property of using a frequency divider is that it will help us clean the signal of our clock oscillator. And so I just picked this data sheet of a random clock oscillator to look at it. And you can see that there's a value here that says output symmetry. And that's actually the duty cycle of the square wave that is output by the oscillator. And you can see that in the case of this model, there's an inaccuracy of about plus and minus 5% at the worst case in the duty cycle of the square wave. And so by using a frequency divider, we're able to clean this up and have a perfectly balanced duty cycle. So one last thing I want to do is to replace this inverter with an AND gate in order to reduce the number of chips that we're going to need in the final build. Okay, so remember how in the first video we separated the ready pin into two separate pins, one which is the wait output and one which is the ready input. It would be interesting to know if our control logic here has to take into account the wait state of the CPU or not. And in fact, you can find this information in the datasheet. If you look at table 5-7, instruction operation, you can find on line number 19D the operation of the wait instruction. So the wait for interrupt instruction takes 3 cycles. You can see here that in the first cycle, ready is 1, and it's fetching the opcode for wait. Then it's taking 1 additional cycle to process it, during which the CPU is not using the databus. You can see here that VDA and VPA are both 0. So I haven't actually talked about those signals yet, but you just have to know that when they're both 0, the CPU is not using the databus. And then on cycle 3, the CPU will bring ready to 0, and it will still not be using the databus. Then once the interrupt is received, it starts back up again, and it fetches the opcode for the RQ or break handler and sets ready to 1. So what this means is the CPU is not actually doing any I/O when it pulls ready to 0. And so we can safely ignore the state with our control logic. We don't actually care about the state of the databus when the CPU is waiting. So if we go back to our signals here and try to interpret what the datasheet table said about the wait for interrupt instruction, you can see here that in the first cycle, we are fetching the opcode. So this is a normal CPU cycle. In the next cycle, we are decoding the instruction. And so during this time, the CPU is not using the bus. But from an outside point of view, it looks like a normal cycle again. Then right after the falling edge of the clock of this second cycle here, the CPU starts waiting, and it actually brings the ready pin low, but it's still not using the bus. So VDA and VPA are still 0. And then the CPU is detecting an IRQ. It will bring the ready pin high just before the falling edge of the clock here. And so the next cycle is a normal instruction fetch cycle. So this shows that we don't have to do anything with the buffer and the latch when the ready pin is pulled low by the CPU, because those cycles here are not actually data transfer cycles. And the cycle right after the CPU starts processing again, it's just a normal cycle. So we don't have to have here retain the value from all the way over here in terms of the bank address, or we don't have to keep the buffer opened during this whole duration. We can just ignore what happens here. And so that means that in our design here, we can actually replace ready by ready in and completely ignore the wait state. So we only want the buffer and the latch to be impacted when we're actually asking the CPU to stop ourselves. There is one final consideration. If you look at the timing diagram of the CPU, you can see that for the ready pin, there is a small interval when the clock is falling where the ready pin is sampled. And so during this interval, there is a setup time and a hold time, which is TPCS and TPCH, processor control setup time and hold time. And both of them are a minimum of 10 nanoseconds. So we need to make sure that during this interval, our ready value is known, because if it were to suddenly change maybe right before the falling edge of the clock, we don't actually know if the CPU would pick it up or not. But the way our control logic is done, even if the CPU doesn't pick up on a change because we did it too late in the clock cycle, the control logic will still be impacted because there is no timing consideration here. And moreover, we also don't want ready to be changing when we are in the first part of the clock cycle, because the CPU will be sampling it at the end of the clock cycle, and so only the next cycle will be impacted. But if we change it here at the beginning of our clock cycle, then during this whole time, our control logic will be impacted. So there is a bit of a consideration here. We need to control the point in time where our ready input is changed. And so the best way to do that is to have it only change on the rising edge of the clock, so that both our control logic and the CPU react in a synchronous way. So for the CPU, if ready pin changes on the rising edge of the clock, then it will be sampled here correctly, and the next cycle will be a wait state. And then for our control logic, if we change ready at the same time as the clock rises, then we are already going into a transfer state, and so the behavior will also stay consistent. So the best way to do that is to add a D flip-flop in between our ready input and our control logic and the CPU. So this is what it looks like. You see that we are clocking the ready input with a clock signal and ensuring the output only changes on the rising edge of the clock. And so we can send this into our control logic for the buffer and the latch, and also to our CPU ready input. And so this will ensure that both the CPU and the control logic react synchronously to our ready change. Okay, so now that we have our control logic finalized, let's look at the timings. So for the latch-enabled circuits, we are only going through an AND gate. And so for this one, I'm going to use 74AC08. And if we look at the switching characteristics at 5 volts, you can see that the propagation delay from low to high is 1 to 8.5 nanoseconds, and the propagation delay from high to low is 1 to 7.5 nanoseconds. So if we change this in our diagram, this is what it looks like. So you see there's a very little difference on the behavior. Let me remove the old one. So this is what it looks like. You can see that we are still meeting the setup time and hold time requirements for the latch, and there's not much impact at all. And so that's because we ensured that there was only a single gate between the clock and the latch enabled signal. So now let's take a look at the buffer. So this is the timing diagram of the buffer where we left off the last time. And so for this signal, we have the same AND gate, so the same 74AC08, and we also are going through an OR gate. And for this one, I'm going to use a 74AC32. And if we look at the switching characteristics at 5 volts, we can see that the propagation delays are actually identical to those of the AND gate. So let's update our timing diagram with those values. So this is the values before. And so this is the new values. So you can see that for the output enable of the buffer, we have quite a bigger undefined state. And so this results in a bigger time where we don't actually know whether the buffer is on or off. And so that's not ideal, but it's also kind of okay because we know that the buffer is off before the CPU starts outputting the bank address. And I already talked about the fact that we have to delay the output enable signal just a little bit to be able to read and write data correctly. And so I already mentioned that we're going to fix this in a future video, so there's no change here. So just know that it takes a little more time for the buffer to register the change in state of its output enable. So now if we take a look at the timing of our bus enable pin, we know that the latch output enable signal doesn't change. We're still using the same NAND gate configured as an inverter. But for the output enable of the buffer, the propagation delays are AND gate plus an OR gate. And so if we look at this here in the diagram, so you can see that this is the way it changes. So it's getting quite long, the time to turn off or turn on the buffer. And if you notice, we are starting to go slower than the CPU because this is 27 nanoseconds here. So this is also something we will have to fix in the next video when I go back on the timings. So now that we have everything, let's update our KiCad project. So I have here our KiCad project where we left off the last time. Let's start by adding the clock frequency divider. Okay, so this is our frequency divider added to the circuit. Let's add our control logic. Okay, so this is the new control logic. Now we just have to add the flip-flop on the ready input. Okay, so this is a flip-flop added on the ready input and connected to a previous ready circuit. Now, one thing I want to do is to replace this inverter with one of our NAND gates because we freed up a bunch, and so this will allow us to remove one chip from the circuit. And so now we just need to annotate all these chips and add the spare gates, and we should be done. Okay, so this should be everything. Let's move on to implementing this on the breadboard. So this is our breadboard where we left off the last time. Let's get started. So the first thing I want to do, since we're going to add a bunch of new control logic chips, is move this one to the second breadboard because it's going to be a bit awkward up here. And then we have removed the inverter from the circuit. So I'm going to rip that out as well. And we're going to start with a brand new circuit. So I have here a 74 HCT74 dual D flip-flop. I'm going to put it here on the left. Bar and ground. And so the first circuit at the top here is going to be our clock multiplier. So I need to connect pin 13 and 10 to VCC. Pin 12 is going to be the ready input. And pin 11 is going to be the clock. And the clock we get from the frequency multiplier on pin 5. Just notice that my ground is in the wrong place here. Pin 11, 5, the clock. And then with a diode, we go from pin 9 to the ready input of the CPU with a 1K pull-up. So the ready input is pin 2. Then we go to the NAND gate that we use as an inverter. So this one needs power and ground. Bring capacitor. So we need to use the first gate at the top left as the inverter. So we have here our ready pin from the CPU that goes into the inverter, and then the output of this inverter goes into the second NAND gate. And to the second NAND gate, we need to bring the output of the flip-flop. So over here at the output, we have the wait signal. So I'm going to put back our LED. So this is everything from the ready input demultiplexing circuit. Then if we go towards the control logic, you have here 74HCT08, which is a quad AND gate. Needs power and ground. And a decoupling capacitor. From the output of the flip-flop, which is here, we need to take this to the input of the AND gate. And we also need to get in the inverted clock. And so the inverted clock we're going to get from our clock multiplier here. So for clock multiplier, we need to connect pin 1 and pin 4 to VCC. And we need to connect pin 6 to pin 2 for the feedback loop. And pin 3 is going to be our clock input. Tie that to ground for now. I'm also going to tie the ready input, which is pin 12, VCC for now. Okay, so let's keep on building the control logic. So from the AND gate of the inverted clock and the clocked ready pin, we go to the latch enable of the latch. And so that's going to be pin 11 on the latch. And we have to remember that the latch is the other way around. The pin here. Okay, so this is our latch enable signal. Then from the same output, we go to the OR gate. And I have here 74HCT32. needs power and ground. And the decoupling capacitor. So I'm actually going to change this a little bit. Okay, so the second signal that we need in our OR gate is the inverted bus enable. And for that, we're going to use the NAND gate here. I will bring it around this side. So this here is going to be our bus enable input, and it needs to go back to the CPU. And on the CPU, it's pin 36. That's this one here. I think I'm going to go the long way around. Here. And down. And so I'm going to move the pull-up of the bus enable pin to here so that it leaves some room on the other side so that I can move this pull-up. From the inverted bus enable, we go to the output enable of the latch. And so that's pin 1 on the latch, which is all the way up here. So I'm going to shift this one over one spot so that I can go through with a wire between those two chips now that I have some space here. Let me go 2 spots. I'm going to take the inverted bus enable and bring it all the way over there. Pin 1 of the latch. And I also need to make a longer wire because I shifted it places. And so the only thing that remains is to take the output of the OR gate and bring it to the bus enable of the buffer. And so that's going to be pin 19, which is this pin over here. Yeah, that should be everything. So the only thing remaining is to connect all the unused gates to VCC. There we go. That's all the unused gates connected. And I'm going to connect bus enable, which is here. to VCC. So we have all our current input signals here. There we go. So in the next video, we'll go back to the timing diagram and try to improve the circuit to make the timings work. And once we have made all the needed modifications, we'll go back to the breadboard and actually test this new circuit. So I hope you enjoyed this one. Let me know in the comments if you have any questions or feedback. And I hope to see you in the next one. Goodbye.